of atoms in a clock is that the laser, when you drive the atoms from the ground to the excited state, imparts a phase that depends on lattice height. That's what we discussed last time, and it gives rise to a spin orbit coupling. So as I mentioned yesterday, the problem is that even if you start with an state that is initially all down and identical, as soon as you drive the state, then depending on the lattice height, you are going to have a rotation that has different phase that differ along different lattice heights. And this, what it does is that if we start with an initially polarized state, it creates a spiral state after the first pulse. This is going to be the dynamics. So there are two ways that we can proceed. One is to start with a state that is in the spiral state. This is one way to proceed and not change the Hamiltonian. Or alternative is to go to a frame where we transform the spiral to a fully polarized state. So the initial state is fully polarized, but then the Hamiltonian is different. So we can do the two cases, and let's discuss them. So one, in order to undo the spiral, if you are going to start to rotate the particles where the initial state is, for example, is in the SY plane, but is rotated around the Z direction by an angle phi, 2 phi, 3 phi, depends on the lattice height, you can see that the simple unitary transformation that transforms this state into a fully polarized state is to have a transformation that is on the form U equal to E to the IC, and then you're going to have an angle phi that depends, or maybe I put SC, that a angle phi that depends on the lattice height. So, or maybe I was using, yes. I mean, in this case, it's less confusing, J, like we put J and J here. So under this unitary transformation, what happens if you do this sigma plus sigma minus IU, then this gives you the next, then a state that is phi plus I, or J, let's put J here. And then you have the state that is E to the minus I, J, phi. This is this transformation, so undoes the spiral. So in this case, then, what happens after this transformation is that we can directly use it to transform the Hamiltonian. Yes, so our initial state is fully polarized, and then what we need to do is to start transforming a Hamiltonian that is initially SU2 symmetric into a Hamiltonian that is going to be not SU2 symmetric. So if I start, the Hamiltonian is going to be proportional, let's put the proportionality, to S plus I Sj minus plus S plus minus Sj plus. This is going to be, this is equivalent to the Sx plus Sy. Except, I mean, there is a factor of 1/2 here. Well, it doesn't, I mean, Sx is going to be S plus S minus divided by I, divided by 2, and Sy is going to be S plus minus S minus divided by 2I. So when you are going to have a Hamiltonian, that is the first term of the Hamiltonian, is going to be proportional, let's put the proportionality, to Sxxx plus Sy plus Sc. Yes. Then the Hamiltonian Sx is going to be transformed. You can transform this term Xxx plus Sy into a spin flips operator that raises and spin flip up and down the spin. So this term is going to be yes, so there is going to be a factor of 1/2 here, doesn't matter, and then you're going to have this Hamiltonian that is SC. But now when we go to the rotating frame, or the spiral frame, where we are undoing the spiral, these operators are going to have a phase, because this is going to have a phase. Remember, there are nearest neighbors. So let me write already the fact that these are nearest neighbors. And therefore, there is a phase. This acquire a phase I phi, and this has a phase I plus 1 phi. So there is a phase between these two that is going to be e to the I phi. And similar a phase that is going to be minus I phi here. And then when you rewrite again these operators in terms is operators Sx, Sy, what you get is that the new Hamiltonian is going to be of this form. So you are going to have a Hamiltonian that has a term that is cos phi. Oh, okay, so let's rewrite it. So you are going to have a term that is going to be cos phi Sx plus Sy. The term SC remains the same, but then you're going to have a term that is going to be sine phi, that you have Sx Sy minus Sy Sx. And for simplicity, many times I'm going to rewrite this Hamiltonian as I'm going to complete the square. For simplicity, is going to be cos phi S dot S, and then we're going to have a term that is going to be, here I'm going to have a 1 minus cos phi SC. So I just complete the square in this Hamiltonian. So this way to rewrite the Hamiltonian is very convenient to understand what happens with the dynamics. So let's look at a little bit of these terms. This term is, people in condensed matter call it a Heisenberg Hamiltonian because it's SU2 symmetric. This term, people refer it as an Ising model. And this term is kind of the antisymmetric exchange Hamiltonian, or I cannot even pronounce this, in Maria interactions. So it's a Hamiltonian that is a little bit weird because you can see this minus sign. It's kind of, it favors spin chiral textures. And this we get naturally by going to the rotating frame. So what happens then when we have atoms in the clock that are going to evolve under this Hamiltonian? If I have a Hamiltonian that is sigma dot sigma or S dot S, and I start preparing a spin polarized state after a pi half pulse, for example, what dynamics this state is going to have? What do you think? If I do, the protocol that we are going to do, I'm going to remind you, we are always going to do Ramsey spectroscopy. So it's going to be, and let's imagine that we are going to stick to pi half pulses. I start all the atoms down. I do a pi half pulse. Let the system evolve for some time t. Then you can do another pi half pulse and measure population. So the idea is that I start with all particles in my Bloch sphere. I'm going to start with all particles down. Then I do a pi pulse, and imagine that I do a pi pulse along the y direction, and then I start a state that is polarized along the y direction after, let's do this, the drive. This is the drive, and then let's write with this color my state. So I start with this, I rotate with a drive, and then there is going to be perpendicular to the drive, and it's going to rotate along the y direction. So I have a state that is fully polarized along the y direction, and I evolve this state with a Hamiltonian that is S dot S, Ij. What happens with the dynamic? What happens? What is the evolution of this state? Nothing is an eigenstate of the problem. You have remembered the characteristic of being SU2 symmetric is that no matter what is the orientation, this state, this Hamiltonian is an eigenstate of the collective spin operator S. So if you have a Hamiltonian that is, you are going to write the spin operator as a square, or S dot S, the collective spin operator, that is sum over ij si dot sj. If you remember, if we are going to look at our angular momentum addition, if you have n particles that are spin 1/2, what is the total spins that I have of this state? I can have S going to be from n/2 to 0, yes? The states that are S equal to n/2 are the states that are fully polarized, yes? These states S/2 have an eigenvalue. When you have these states, we are going to rewrite this state with S equal to n/2 as decay states. Their total S equal to n/2, and they can have a magnetization MC that goes minus n/2 to n/2, yes? And these are, if you are going to have, these are eigenstates of this Hamiltonian with eigenvalue n/2 plus 1, yes? So it's an eigenstate. This Hamiltonian, even though this is not all-to-all, I'm not summing over all-to-all, but I'm summing still over nearest neighbor, it doesn't matter. This Hamiltonian has the symmetry that is SU2 symmetric, therefore an initially polarized state is an eigenstate of the problem. So if I put this state on, then nothing will happen. Physically, why is nothing happens? Remember that if I have, as I was mentioning before, is I have a state that all the atoms are spin polarized. Can they tunnel? No. Because of Pauli statistics, this atom cannot move to here, so the atoms are going to remain there doing nothing. The problem is because of a spin-orbit coupling, we are going to get these extra terms in the Hamiltonian. And these extra terms are not SU2 symmetric, and they're going to give rise to dynamics. Yes? So, okay, this is one reality of the experiment. So we are going to have to deal with the dynamics of these extra terms. And moreover, the experiment is done in a lattice generated by laser beams. And laser beams are Gaussian. They have a Gaussian profile. So we cannot, unfortunately, consider the system is a box. Unfortunately, the Gaussian profile imposes an harmonic oscillator on top of the system, and the system is going to look like this. The atoms are in an harmonic oscillator, and there is going to be an energy penalty to move from one lattice side to the next because of the harmonic oscillator confinement. So let me ask you, we are going to have maybe the easiest way to try to understand the dynamics of the system under this Hamiltonian is considering the case where you are going to have phi it's equal to pi. And let's start, as I said, we can go and look at this Hamiltonian, or we can start with a spiral state and look at the dynamics. And let's start by looking at two sides, only two sides. So if I have a spin-orbit coupling phase pi after the first pulse, I'm going to imagine that in this case the pulse is along, for simplicity, because I don't want to write complex numbers, the drive is along the y direction, and the state starts polarized along x after the rotation. So then the initial state is going to be given by a state that is pointing along x on this side, and because the spin-orbit coupling phase, this state is pointing along the other direction in the next side. Now, in this basis, if I have a Hamiltonian that is 4j squared over u, S dot S, then what I want to ask you, if I do this protocol of Ramsey spectroscopy, and what I measure is the length at the end of the protocol, imagine that what I measure is the length of the spin, S minus. This length of the spin, S minus, is going to be the length of the expectation value, the expectation value of S1, the first particle minus, plus the second particle minus. If I measure the expectation value as a function of time, what I'm going to see. And I will let you compute that, because this is the tutorial session. So let's start by doing computing what you expect to see. So any conclusion? Anyone interested in going to the blackboard and sketching the idea? Too early? So what could happen? There is only one energy scale in the problem. There is only one energy scale. Which one is the energy scale? This one, yes? This is the energy scale. So the only thing that can happen is oscillation at this energy scale. There could be anything more in this problem, yes? So basically, we're starting, again, go back. What are the eigenstates of the Hamiltonian on this problem? We're going to have the triplets. we can put a constant here to make the energy zero. Doesn't matter. These have energy zero. And the singlet, the triplets, and the singlet that has energy for J squared over U. Yes, that's the only thing. Now, if you look at this initial state, this state is going to be up plus down, this guy, our first particle, and the other particle is going to be up minus down. Yes, because it's in the other opposite direction. So we're going to have a state that is going to be a superposition of up, up. Then you're going to have a superposition minus down, down. And then you're going to have a superposition here that you are going to have up, down. And then plus down. Yes, this is my initial state. So what happens is that if I look at the dynamical evolution, when I look at this state after I apply the Hamiltonian, what happened? This is going to acquire no phase. This is going to acquire no phase. And only the put a plus here. I put a minus. This is, I'm going to put a minus here and then minus here because this is plus. The singlet is going to have a phase, and a phase that is 4 J squared over U. Yes? And then what I compute the contrast, what it compute S minus, the S minus is going to try to look at the population of the triplet states, because the singlet state has S minus equal to 0. So basically it's the population of the singlet states, and the population of the triplet states are going to have, when I look at the expectation value of S minus, I'm going to have a quantity, this is going to be a quantity that oscillates, that is going to have something that as oscillation frequency that is going to be proportional to cos 4J squared over U times T. So that's the type of oscillation. We are going to see an oscillatory dynamics on the system. So that's expected. In contrast to when you have in the contrast when you have just spin orbit coupling equal to 0, where your initial state is here is plus, and then there is no dynamics. In this case, we have an oscillatory dynamics. Now, in the experiment, there is an additional issue that, this is oscillations in this principle you are going to happen at frequency U. But in the experiment, what happens is that there is the harmonic confinement that makes the super exchange between different sites not equal necessarily to 4J squared over U. What happens? So if you have one particle here and one particle here, if we are going to see the two different processes. So imagine that I have an atom here that is up, an atom here that is down. When this particle hops into this site, then what is the change in energy? So if this is delta, let's imagine that this quantity is delta. When we are going to do the second order perturbation theory, that for example, I'm going to see, I have an atom that is up, down, and then I'm going to add here the tunneling Hamiltonian. I'm going to have the intermediate state, the Hamiltonian, and the final. So what happens is that if I'm going, for example, when this atom is going to tunnel here, what is the final the intermediate energy? So the intermediate energy is going to have, so it's going to, the intermediate state is going to be the state up, down, 0. This is going to be the intermediate state. And this state is going to have energy what? This state, when you are going to go from, if this has energy, this state has energy plus delta, this has energy minus delta. When this is going to tunnel, not only you are going to gain energy U, but you are going to change, and you are going to have the tuning gain in energy, because you are going to have plus delta to minus delta. So maybe we can put the delta half to avoid factors of 2, yes? So you're going to have an energy that is U minus delta. But when you are going to put, this is when you tunnel here to here. But when you tunnel from here to here, what happens? You are going to, this is going to, yes, you are going to have energy, the initial, let me write it here. So the initial state is going to have 2 particles here, and then you're going to increase energy U and decrease energy delta, yes? In the other case, when you go to, and then you're going to have the 2 particles here, you are going to increase energy U, but also increase energy delta, yes? So the second term, when you're going to tunnel to the state down, up, has a denominator that is, this is the J square, yes? And then there is the J square, and then the other half denominator, U plus delta. So you have the 2 processes going into play, and that's why the super exchange interactions is going to be J square U plus delta plus U minus delta, and therefore is going to be proportional to J square U divided by U square minus delta square. So, but the point is that this, and this is what is written here, and the point is this delta now is not uniform across the lattice side, because the harmonic potential is in the form, the Hamiltonian of the harmonic potential is the form sum over Ni, or let's put N, N, or J maybe, J is better, J, a term that is quadratic in J, is proportional to that. So the difference between atoms in different square minus J minus 1 square. So this quantity, I'm going to put a J dependence, and therefore this introduces oscillations between 2 particles per side that has going to have a different rate, and this is going to introduce dephasing. Yes, so in the experiment, what we are going to expect to see, although of course the calculations are going to be much complicated because they not necessarily have only 2 atoms next to each other, the idea is that if we do a clock experiment and let the atoms tunnel in the super exchange regime, because of a spin orbit coupling, we are going to have dephasing. So let's see what we see. So this experiment was done, was published this year actually, and what the experiment started is by having atoms in a 3D lattice. Very cold fermions in a 3D lattice in the lowest band. And what we do, again, these are the clock states. This is nuclear spin polarized. We log the particles in the lattice, and as I said, the energy scales are U, the different energy between the different lattice sites, and the tunneling. Now, well, besides the dephasing, because the spin orbit coupling induced super exchange modifications, there are other systematics in the experiments. The experiments are never perfect, homogeneities, other things. So in order to avoid single particle decoherence, they implemented what is called SYC decoupling, SYA decoupling. So that means, what it means, SYA, is that they apply A pi pulses that are driven to avoid dephasing. So because spin echoes is so fundamental for everyone, so let me review a little bit what a spin echo is, so for you to understand the power of this method. Have anyone here worked with the spin echo pulses? Yes? So the idea, let's do it for 2 particles. The idea, if I have a Hamiltonian that is H1 S1C plus H2 S1C, H2 S1C. So there are 2 spins, and each spin is precessing a different rate. this is processing at rate H1, this is processing at rate H2. And I want to do a Ramsey protocol where I prepare, I'm going to write it in the YX plane of the block sphere. This is for spin 1, YX plane for the spin 2, spin 1 and spin 2. So imagine that at time equal to 0, I put my particles in the XY plane, pointing along the X direction. So my particle is along this direction, this particle is along the X direction, time equal to 0. Then I let my system evolve for some time t. So what happened? This is going to acquire a phase, this is going to move because the rotation axis is now along the Z direction. So my spin is going to precess, and I'm going to accumulate, for example, a phase that is going to be H1t. And this is going to be after this time. And then this other particle, because have a different precession rate, is going to go to H2t. And then when I'm going to sum what is the collective spin along the Sx direction plus Sy direction is going to be reduced because they're pointing along different directions. So it's going to introduce dephasing. How I'm going to remove the dephasing? What we do is what is called spin echo protocols, that I apply a pi pulse in the middle of the dynamics. So if I apply a pi pulse in the middle of the dynamics, what happens is that, imagine that the pi pulse is along the X direction. If I do that, the X component of the spin, so this is the spin that I have after half of my evolution, then the X component is not going to be affected, but the Y component goes from plus to minus. So after the pi half pulse, then this disappear, and I'm going to have an state here. And for the other, the same. After the half pi pulse, the X component is not affected, but I only to have my new spin, the same X component, but just down. And then I let the spins evolve for the same amount of time. Yes, I continue evolving for the same amount of time. So if I continue evolving for the same amount of time, then this is going to move H1t, and the other is going to move H2t. And after this time, everyone is going to be pointing along the same direction. So I cancel the decoherence. It's like this Hamiltonian never existed. This is pictorially. Mathematically is even simpler. Mathematically, what I'm doing is that if I have a Hamiltonian, mathematically I have an initial state. I let the system evolve with the single particle Hamiltonian. This Hamiltonian is the sum of this term here. Then I'm going to apply a rotation along x pi direction. Then I undo the Hamiltonian. If I let the system evolve for another amount of time equal to this. And for example, I'm going to make sure an observable that is Sx. So you have the same initial state, e to the I SCT, e to the I Sx pi, e to the I SCT. So what is going to happen is that this, when I'm going to apply, I mean, I can always, because it's a unitary operation, I can sandwich here a term that is e to the I Sx pi, minus xx pi, e to the I xs pi. Because this is nothing, this is the identity, yes? And I can sandwich here the same thing. I can add e to the x pi, and then I'm going to have, what is going to have, sorry, this is the first half, so I'm going to have this term here. this term here, and I'm going to have this Hamiltonian here. And then I can do the same here. So I'm going to have e to the I x x pi e to the, sorry, here, e to the I sx pi e to the minus I sx pi. So you can see that when I look at this evolution of this term, I'm going to have a rotation of this Hamiltonian by pi half. And if I rotate SC I'm doing a rotation of S along Sx by pi. If I rotate along x by pi, this Hamiltonian acquire a minus sign. So I'm going to have e to the SCT, and this part becomes e to the minus SCT. So they cancel. Yes, and same in the other part. So you're going to have, in this case, you're going to have this Hamiltonian. There is e to the, is a rotation of xct along the pi direction, along the x direction by pi. So these terms here, this term here is going to be e to the minus I SCT plus, that is going to cancel the other evolution. So this cancels the dynamics. And then as a whole, I have no dynamics evolution of the initial state, and that's very good. So of course, this is good and completely remove any type of inhomogeneity that is static. Yes, because that is not changing as a function of time. If you have an inhomogeneity that is changing with time, it's a problem because this doesn't work. So in order to remove inhomogeneities that change in time, you don't need one pulse, but you will need many pulses. And that's the beauty of this SY8 model. You can see you are applying a few pulses, 8 pulses along the different directions. One along X, one along Y, one along X, one along Y. And people from NMR has shown that this is the best way to actually remove decoherence. Single particle decoherence. Yes, is that clear? So, well, that's the sequence that I apply, and this is what the experiment measure. When they measure the contrast of the length of the magnetization as a function of time in the experiment, indeed, they see the decay of the magnetization. So in this case, to measure the contrast, one thing that they were doing is that they compared the ticking rate of some part of the cloud, P1, compared to the ticking rate of the other part of the cloud. And they look at how different, they look at how the population in these two different parts of the clouds after the pi half pulse of the Ramsey sequence is how they evolve. And then if they are identical, then nothing happens. But when they're not identical, I mean, this is what they fit, the population second of this part of the cloud compared to the other. And the contrast is going to be the length of this ellipse. Yes, if they're going to have, if they are ticking identically, one respect to the other, there is this line, and the contrast is going to be the length of this line. If they start to shrink, as it does here, you can see that the contrast is decaying as a function of time. That's the way that they were fitting. The experiment is called ellipse fitting. That is becoming one of the most popular ways to actually look at differential sensing between two parts of the cloud, between two ensembles. So let me tell you a little bit of what the experiment did in this case. So what we did is that we are going to revisit all the prior experiments that we did when we were doing only lattice along one direction. So this is the lattice, and now we have a 3D lattice. So we have lattice along X, along Y, and along Z. So if there is not lattice here, so here is the lattice along the perpendicular direction. So if there is no lattice along the plane, and the only lattice is along the Z direction, in this case, we are going to recover this set of pancakes, yes? But as we move along this direction, we are going to start to add some corrugosity in the pancakes. More corrugosity, more corrugosity, more corrugosity, until if we are going to have a very tight confinement in the XY plane, we change the geometry to an array of tubes, because now we have a very deep lattice, like an egg cartoon in the XY direction, and the cloud is going to be kind of an ellipse yes, and only weak tunneling along the Z direction, so we grade this. And if we go back to this very deep in every direction, is kind of point systems where nothing tunnels. Yes, is this clear? So what we did in the experiment was trying to we fixed the confining along the Z direction and start to move, change the lattice along the plane from very weak lattice to very deep lattice. So basically go from here to here. Why they did that? Because they were very kind with theories. We cannot solve dynamics in 3D. And so what they did is trying to restrict the dynamics to tubes where we can solve the dynamics in a 1D system. That somehow is not so hard to do. Yeah. And they look at the contrast decay in this array of tubes, and we were trying to simulate the dynamics of this bunch of tubes. As we go along this direction, as I said, we are going to start to squeeze the Warner functions in the XY plane and make them more elongated. That's what we do. The tunneling along the Z direction doesn't change, but the interactions change. Yes, the tunneling along the Z direction, along this direction, the lattice depth is remain fixed, so the tunneling rate is not changing, but what is changing is the interaction. So this is the summary of the experimental observation as we go from shallower lattice to deeper lattice. And you can see these oscillations, the contrast decay, and there is a little bit of oscillation characterized by the average of this spin orbit coupling parameter. So this is the experiment or these dots, and you can see that there is you go to, this is a little bit shallow lattice, this is deeper lattice. The problem is that the experiment was not unit field. They were parts where the experiments have holes. And having holes in a hover model is very complicated because it gives rise to what people call TJ model. Because while holes can move at tunneling rate T, or J, the super exchange is J squared over U. So if you have some dynamics of J squared over U that is slow because J is smaller than U, tunneling can be very fast. It can dephase even more the system. So this is what happened here. We're going to have the dynamics of the system. But anyway, and also there is the inhomogeneity from the one lattice side to the other. But we can see that overall, if we do the theory based on these parameters, we can see that all these curves, depending on the lattice depth, are going to fit into a very universal curve that is telling us that we do see super exchange interactions. So it's the first time that we see coherent super exchange interaction in the systems. So there has been many other experiments looking at super exchange interactions, first starting by Emanuel Bloch and many other experiments, but they were never seen the coherences between the spins. They were always measuring populations. Here, because we are doing a Ramsey spectroscopy, what we are seeing for the first time is the emergence of coherencies driven by super exchange. And of course, you need a spin orbit coupling because if you start a spin polarized state, nothing happens. So Wolfram Ketterle had in the past, I hope I'm citing these experiments, Wolfram Ketterle have in the past experiments starting with a spiral state, no spin orbit couplings, but a spiral state. And of course, beautiful experiments by Emanuel a few years ago when they see super exchange, but this is the first time that we can see super exchange in a clock. And with coherences, Okay, now, as I said, we can even increase the number of holes, and therefore with a laser, you can remove some of the number of particles and make the system more dilute. And we can see that the larger the number of particles, you can have largest contrast decay because, well, the system is more dense for large number of particles, and you can see that the contrast as a function of time decays faster the more dense the system is, as expected. If the system is very dilute, then if you have holes, the holes don't necessarily have too much contrast decay because they are just moving without affecting too much the dynamics. Except, of course, the spin orbit coupling modifies a little bit the behavior. So, but okay, so this is this finalizes kind of the experimental exploration that we have so far. So what I'm giving you from this to the next few minutes, and then we go to more exercises, is an overview of what is the vista ahead. I mean, theories can dream before experiments, and I give you an overview of the vista ahead and what the neat physics that we think we can see in this type of systems. Um, so back in 2010, we wrote a paper saying that alkaline atoms have SUN interactions. And then after writing this paper, there was a slew of other work that actually motivated by this paper that predicted that SUN symmetry can give rise to very exotic type of phases. For example, I'm going to give you some idea of the type of Hamiltonians that we can implement. So if we restrict to atoms in the ground state, not excited state, only atoms in the ground state, we are going to have a system that has SUN symmetric interactions with many flavors. So if we have, if you have, as we saw recently, I mean, at the beginning and now, I mean, this part has been focusing of spin 1/2 particles, and we saw that the superexchange interaction was in the form S dot S. Mm-hmm. And Suber-Sachdev was telling stories about this, that this gives rise to an antiferromagnetic phase, singlets are formed, is magnetically ordered. But if you go from a spin 1/2 to a spin I, for example, a spin I that is 9/2, when you have 10 different flavors, here 2 flavors from 2 to 10, then numerical calculations have shown that when you are going to increase the number of flavors, you are not going to remain ordered, and for n larger than 5, you are going to start forming spin liquid states. Chiral spin liquids is predicted from theoretical calculations to be the ground state of an SUN Hobart model or super exchange, the equivalent of super exchange model in SUN magnets. Mm-hmm. So for a spin, for a spin 2, a spin 1/2, then you can form a singlet between two sides. For a spin 3, so you're going to have this spin, 2 flavors. For 3 flavors, you are going to form in a square lattice, you can form some type of order within the plaquettes, some type of like that. For a spin 4, you can form spin singlets between, these are the different flavors. So for example, red, blue, green, brown, so different flavors, 4 different flavors, I call in red, blue, green, apple, I don't know, 4 different flavors have formed an SU4 singlet. But when you go beyond 5, it's not possible, and it seems that the system forms a chiral spin liquid. So this has not been seen. These are just theoretical predictions where you are saying, well, after here, when you have a spin 5 and beyond, we are going to have spin liquids. It's a lot of theoretical predictions. If you are going to have states that are systems in which you can create different lattices, a lattice that is much deeper for the excited state and shallower for the ground state, you can form what is called Kondo lattice models. Kondo lattice models are models in condensed matter when you have coexistence of localized magnetic moments with mobile particles. And actually the mobility of the particles is the one that introduces, make the particles more heavier and generates what is called heavy fermion materials. So there were some predictions that we can do this type of heavy fermion physics of Kondo in the system. And then when you have Hamiltonians, that you have 2 different type of spin states and 2 different, or many times of different type of spin flavors and two orbitals. In condensed matter, they call this model Kuhel-Chomsky models, and they give rise to really the rich physics of transition metal oxides. So the physics can be super rich and a lot of things to explore. So let me tell you an instance, a hint, very, 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 very basic of the Kondo lattice model. So in the Kondo lattice model is a model where you have localized magnetic moments. These are associated with the F electrons. You can see these purple ones that are coexistent with a band of mobile electrons. These are the red ones that are delocalized. They can tunnel. So the Kondo model tells me, well, my delocalized electrons can tunnel, and they are labeled with C spin operators. They are fermionic spin operators, and I have the F electrons cannot. They are just the tunneling is zero. But on the other case, there are going to be exchange interactions that are local between the F localized electrons and the conducting. That's the Kondo lattice model. So you can, on site, you can have flip-flops that we already studied them. So on site, in a given lattice site, oh, this is not good. In a given lattice site, now if this is the ground, for example, and this is the excited, and then you have down and up, then you have processes when you can do a spin flip. This goes here, and this goes here. These flip-flop processes inside. This is the S dot S term. So you can see that we do have this term, and we can have the tunneling, but the problem is that typically we have assumed that we have magic lattices at the moment, that the ground and the excited state have the same matrix. Well, going back, but before elaborating more into the boson, the implementation in alkaline air atoms, similar to the phase diagrams that Subir was showing in his lecture, heavy fermions and the Kondo lattice model seems to be, the phase diagram seems to be extremely rich, and these are still not understood. They said that depending on the ratio between the exchange and the tunneling, you can have from antimagnetic order states, antiferromagnetic order, to heavy fermions, and in the coexistence between the two, some exotic superconductivity. That's what is predicted, a lot of controversy and not so well characterized. The hint of the, a little bit of understanding of why you have what is called heavy fermions is very simple. If you treat the interactions as a perturbation, if you write the energy levels or the dispersion relation of particles that are hopping in the lattice, they have a dispersion relation that is 4J cos K, yes? K the quasi-momentum. So if you have particles in the lattice, you are going to have an energy that is, this is a cosine, that is this 4J cos QA, and let's put this Q, yes? This is the kinetic energy, the dispersion of particles that hop. The localized particles cannot hop, and the localized particles, therefore, have energy zero. So these are my localized particles. And what happens is that there is an additional term, the interactions, and the interactions always act when there is degeneracy. If the two particles are very similar energy, the interactions couple them. It's an avoided crossing. So basically, the interactions at the points that the energies are the same, then the interactions at avoided crossings. So you can see that a band that was having a lot of curvature, after you add the interaction from the Kondo lattice model, then the new band becomes like this. And therefore, when you start to fill your particles, because they are fermions, and you have to conserve, of course, the number of particles, the Fermi energy, you start to fill, and the energy, the Fermi level, always ends up in the region where the tunneling or the kinetic energy is almost zero. And therefore the particles, because the kinetic energy is a measurement of the mass of the particles, so if you are going to say the tunneling is a measurement, is inversely proportional to the mass of the particles, because at the end the particles are going to, the particles at the Fermi level that are the ones that are going to do the dynamics live here, and they have no tunneling, they are super heavy, and that's what they are called heavy fermions. So this is a little bit of the phase diagram here in this heavy Fermi material. And so in one case is dominated by exchange. Of course, then you form Kondo singlets in this antiferromagnetic state. You are going to have Kondo singlets in each lattice side. So here in this regime, you are going to have instead these states that are a superposition of this state plus this state. This is Kondo singlets in each lattice side. Then as you move to this region, you have the Kondo, and in the intermediate, this is the critical region that Subir was talking about. It's very complicated. I'm not going to cover, I don't understand any of this, but it's supposed to be very, very rich physics to be not understood. So the implementation in alkaline atoms that started to be done in Emmanuel's block group, but it was a little bit stopped because remember that I told you about the orbital Feshbach resonance in the system. Unfortunately, they were lossy, and therefore it was a little bit of discouraging to, not easy to do that, but the idea of this model started to be done there, and I think Takahashi in Japan, in Kyoto, they're trying to start building this type of experiment, is that you want to have conditions in which you have lattice wavelengths that are called zero lattice wavelength. That is a wavelength where the ground state feels a lattice and the excited state no, and vice versa. So under these wavelengths, magic wavelengths, you can engineer conditions where you can generate two different lattice potentials for the particles. So in this case conditions, you are going to have a condition where you are going to make a deep lattice for the ground state, for the excited state, and they are going to be the role of the F electrons, and a very shallow lattice for the ground state particles that are going to be the delocalized particles. And that's the idea. So, and we can try to compute, you can manipulate the strength of the exchange interactions, because these two lattices are independent, if you are going to displace one lattice, then the exchange interaction is the overlap between the two particles, and if you look at this, the overlap is going to be reduced. So there are going to be ways that you can manipulate the exchange interactions, and therefore you have a way to control the phase diagram of the system. So, I mean, this is very long time ago, but I mean, nothing has been realized yet, but hopefully in the next years we start to see some revival of this type of physics. Now, in this last part, I'm going to tell you a little bit of spin orbit coupling with interactions. I mean, in principle, they are going to be useful for generating spin squeezing states, but Nicolo is going to talk about the spin squeezing, so maybe I'm going to skip that part. And then I'm going to tell you a little bit of how we are going to use these systems for generating cluster states. Who knows what is a cluster state? Okay, so I'm going to explain what is a cluster state, and then I'm going to tell you a little bit how we can use this interaction to generate cat states, very briefly. And then but it's a tutorial, this part, so maybe I will let you work most of this, because it's not so hard. So for cluster states, what I want you to work out is the case where we go back to super exchange in alkaline atoms, but imagine that we can tune the phase phi to be pi. So we have a Hamiltonian where you have the tunneling that is identical for both ground and excited states, a tunneling. And then I have a Hamiltonian that is U and E and G at side I. And I have a drive. But now the drive has an spin orbit coupling phase. So the drive is going to be e to the a k, let's show over n. So a to the n pi. And then you're going to have a state that you destroy a particle in down in lattice side n and create a particle in up with lattice side n plus complex conjugate. Mm-hmm. I'm going to work in the regime where J is much smaller than U and omega. Mm-hmm. This is the regime. Mm-hmm. Tunneling smaller than J and U, and then but in contrast to before, where omega was very weak, I'm going to keep omega all the time during the dynamics, the drive that is transferring spins down to up all the time, but it has a phase that is changes by pi every other lattice side. Is it clear? So what I want you to try to understand, to try to think about what is derive again the super exchange Hamiltonian in these systems. We already derived it. We already derived it when we have not this term, yes? We already did it. So the task is to rederive it, but when omega is finite and large, can be comparable to U. I give you 5 minutes to think about it. And if you wanted to discuss with your neighbor, that sometimes is useful. If you prefer to work it by yourself, that's also okay. Okay, I'm giving you a hint there. The first hint is that I telling you rotate coordinates. I already giving you that hint. So, yeah. So basically, this Hamiltonian, maybe you can rewrite this Hamiltonian as, this Hamiltonian can be written or X. Yes, because e to the I pi only have values plus or minus 1, yes? That's the phase, and the phase is pi. Let me start you to give you some hints to make the problem solution easier, so you don't have to do formal calculations. Is this stream SU2 symmetric? Yes, because the atoms, the tunneling is identical for the two, so it's SU2 symmetric. Is this SU2 symmetric? Yes, this is the Hobart model, it is the SU2 symmetric. So I can rotate my basis, and instead of pointing this Hamiltonian, I do a rotation of the spins, where I rotate x to z and c to minus x, and the Hamiltonian is going to be identical. It's going to have the same eigenvalues, yes? So this Hamiltonian now, in this new basis, everything is going to be the same, yes? I'm going to, in this basis, the only thing that is going to be different is that it's going to be z, that you know how to deal easier, yes? This is going to be z. So that means if you look at the eigenstates, let's start looking at the eigenstates of two particles in two different lattice sites. This is lattice site n, and this is lattice site n plus 1. If I look at the eigenstates at lattice site n, what I'm going to have is that in this case, this is going to be down, and this is going to be up, and this is going to be separated by an energy omega, yes? In the next lattice site, because there is a minus sign, is the opposite. In the other lattice site, this is going to be down, and this is going to be up, and this is going to be omega, yes? So on this basis, on this new setting, then you can start thinking about super exchange. So you can start, so what we can do is that we can start drawing all the possible configurations, and we can see what happens. So as I did before, we are going to start maybe pictorially. I'm going to start doing the possibility. I can have this up, up. This is one case. I can have, sorry, I can have this down and this down. I can have up, here, down. And I can have this is down, and this is up. Yes? And then you can try to look at the dynamics and see what you get. Remember, tunneling is SU2 symmetric. All right, so can this stay tunnel? No. Spin polarized. There is, if this is tunneling, it has to preserve the tunneling, the spin. If this goes to here, it's already a particle, so no tunnel. Can this stay tunnel? No. Now, in this case, I'm not splitting singlet to triplet because there is an inhomogeneity between the second lattice sites. So let's look at this process itself. So this is up. Remember, this is the only way that this can tunnel is here. Yes? So if the initial energy of this, I mean, let's put this as placing omega. If the initial energy of the state is 0, what is the final energy of the state, or the state of the intermediate state? When this tunnel is here, the energy is going to be what? I'm going to increase the energy by U, but I'm going to decrease the energy by omega. Now, in the other case, that I'm going to do something like this, and if I'm going to do something like this, well, it's the same. Yes, you are going to always do that. Now in these other configurations, when you are going to have something like this, what happens? If this goes here, then you are going to increase your energy by U, but now you are also going to increase your energy plus omega. So now if U, as I said, U is comparable to its omega, this got a lot of energy. That is U plus omega. It's a lot of energy, whereas this one is not. So what happens is that this particle is going to come here. So we're going to have here. This particle cannot go down because it changes the energy of the system. So the only way that, because these are, if the initial state has energy 0, and I have to go back to a 0 energy state, so the only way that this happens is that these particles come here and have to go back. That's it. So the Hamiltonian, therefore, doesn't do any spin flips. The particle, the only thing that happens is that this goes here and this goes here, and that's it. So a Hamiltonian that doesn't have spin flips is an SC Hamiltonian. And SC Hamiltonian, and you're going to have an energy that is J squared, and then you're going to have U minus omega, basically. You can work out all the details, but at the end, what happens is that the states, you are going to have, if you want to be more serious, you're going to have, well, the states that are up, up, the states that are down, down, and the states that are down, up, are going to have no interaction, so you can add some single particle SC terms. But overall, the idea is that there is a Hamiltonian that doesn't have spin flips, and the process that is relevant when these particles go from here to here had a denominator that is U minus omega. Yes? This is what happened here. This is what I'm showing here. So this is a picture of the states. You are going to have the states that has, these are the picture of this state. This has minus omega. These are Pauli block and cannot do anything. This state plus omega, and these are the double occupied states that has energy U. And well, that they are separated by an energy U from this. So I'm just trying to rewrite this process. This has energy J minus U minus omega, and then you are going to have and then that's the term that I'm going to, okay, I'm keeping, you can keep all the terms, but at the end it's going to simplify to that. So you can keep this term here and add a U here. But at the end, if U is equal to omega, is what I wrote, yes? So this is the Hamiltonian. We have an Ising interaction. It's an Ising interaction between nearest neighbor particles. Is this form for omega of the order of U. And this is a Hamiltonian that people predicted a few years ago to be fantastic resource for quantum computation. Why? Because this Hamiltonian generates what is called cluster states. So a cluster state is nothing else. The definition of a cluster state is very simple. It's a state that you create by evolving the system with an Ising Hamiltonian and then stopping it at some time, a specific time. So basically, the cluster state is a Hamiltonian where you start all the particles along the x direction. You evolve the Hamiltonian by, you can ignore the pi poles because it's just to remove single particle decoherence. It doesn't do anything with the SC term. So it's an evolution of the Ising interactions by a time that is proportional to pi divided by JCC. At this time, you create a state that you start everything along the x direction, and along this, when you evolve until this pi, you are applying C0 gates consequently into each of their particles, and this state is supposed to be highly entangled. So entangled that if you have a system that is not 1D or 2D but 3D, is a universal resource for quantum computing. And what they propose in this very famous paper by Briegel is that if you create these cluster states, you can do any gate by measurements. So basically you create the states and then you do gates by just measuring different type of spins, and then this generates different type of operations. But you don't have to do anything else. So in the standard form of quantum computation, you start an initial state, you do a gate, and that the gate is the manipulation, and you create your final state. In this one-way quantum computing is that you create a cluster state, and everything that you have to do after that is just measurements, nothing else. So they believe that is going to be something that could be very useful. For the case of clocks, it's going to be fantastic if it works, because the operations are so slow that the only time that we need is to prepare this initial state, and after that, the only thing that you do is measurements, and measurement can be much faster. So this could be a feasible way to do quantum computing in alkaline atoms in the future. What this state is characterized by some type of stabilizers, that is the product, a stabilizer at atom for atom J is the product of Sx for this atom J and the C in all the neighbors. That stabilizer, so a cluster state is characterized by a state that has stabilizers to be 1. That's the characteristic of the cluster state. And I mean, or the state after you prepare the state, after that and you compute the stabilizers, you can show that is 1. 2 points. In ultra-cold atoms, when people look at super exchange, and as I was mentioning before, one of the big troubles or complication is that it's very hard to have a full unit system. And therefore, the problem typically in experiments is that if you have a system with a hole, if you have a system with a hole, this is spin up, this is spin up, this is down, and a particle is going to move, it causes tunneling energy, yes? The tunneling energy is J, and super exchange is J over U, and this is smaller than 1. So tunneling is going to disrupt the dynamics because it's super fast. The advantage here is that this will not happen. Why? Because if you have a particle here and has to tunnel onto here, what happens? It has to reduce its energy by omega, and this is not necessarily easy. Yes, so the tunneling is not going to happen because you are suppressed by omega. And therefore, the holes are not going to be mobile. And if the holes are not mobile, they are not going to diffuse across your system, and they are not going to screw up your cluster state. So these are the calculations that we did when we add a small system and we add a set of holes, let the system evolve, the holes remain pinned, no dynamics, and therefore we can show that it's going to be very robust to holes. We can generate cluster states through holes. So we are getting all tired, so let me give you a little bit more very quickly about CAT states. We can also create CAT states in this protocol using a spin orbit coupling, and CAT states as a result are a result for metrology, are a result for error corrections. I mean, CAT states are super fragile. I mean, super fragile, but they are very useful states. In principle, you can create. So the question is how we're going to create cluster states in our system. The advantage that we have is that here we're going to focus in the state. Let me rewrite it bigger. You're going to focus in the state. So remember that I was saying this is up, this is down, this is down, this is up because of the spin orbit coupling when the phase is pi, yes? So if I have, sometimes we prefer to relabel, this is for notation. You prefer to relabel the state with have high energy as up and lower energy as down. So we can relabel this as up in this side and this up in the side +1, and this is down I, and this down So it's just for notation. So you can, this is the way that we are relabeling the states. But imagine that I have an initial configuration where I have a state here and a state here. And now let me go to the regime where U is equal to omega, exactly equal to omega. So what happens? When this particle tunnel here, this initial state has, we put the zero energy here. And then what we're going to go here is that this, this is energy omega. So this initial state has energy U, but loses energy U omega, so has initial energy zero. So these two states are resonant. So the particle can tunnel no matter it's in energy cost. So this is going to be our building block for preparing a cat state. So what we do, we are going to have atoms in this harmonic oscillator potential, because always there is an harmonic oscillation potential in the lattice. And what we are going to prepare, all the particles in this dress stay down. You can see down, down, down. This is our initial state. And then what I'm going to do is that I'm going to try to generate a pulse where this particle is going to hop from this side. This is now this label is the single particle energy. Remember, the single particle energy goes as lattice side square. So this is 1, 4, 9, 16, 25, yes? So the idea is that I start everything in down. So now the point is that I'm going to have this particle, and I'm going to have this particle can go to this state from down. Remember, this is the only process that is going to be, so we're going to start to look at the process where I'm going to start this particle here. We are going to start with this particle here, everything in the ground state, and then this has to tunnel here. This has to tunnel here, the only thing that can happen but costs energy. So I'm going to change my detuning, and I'm going to add through the laser the enough energy for this particle to tunnel. So this is the first step. I add the frequency at the tuning of my laser, that I make this process that typically is of resonant by my laser. So I create a state when I have, you can see I have a state to a doublon in a given site. Now I lay the system to tunnel, but you can see that now this particle is going to, again, you are going to start, this particle is going to, you are going to have this particle here, and then you are going to have this particle is going to tunnel to this other side. And then I'm going to, now this is double occupied because it has the other particle, and I'm going to, with my laser, I'm going to have the enough energy to this particle to move here. If anything else can move because the energy changes from one lattice side to the other, so the only resonant process is the one that I give you in my laser. So I'm going to start with this doublon, and I'm going to make the laser resonance for this goes here, yes? For when this go here, this particle is going to start, you have the doublon here, this go here, and then you are going to have the doublon is transferred to the next side, but this other particle remain in this state up, yes? It remains there. Now, when I did a pi half pulse, I create a superposition of this particle coming here, but this particle not coming. Yes, a pi half pulse is a superposition. So half of my state is in this state, and half of my state was in this state. Yes? When I did the laser, when I applied the laser at this frequency that makes this particle hopping here, this particle cannot hop in here because this will be of this particle cannot hop in here because it's of resonance, because it's going to cause energy U. Yes, these have already the energy U, but if this goes here, it's going to have the energy to have a double occupied lattice side. So it doesn't happen. So then after this first process, this remain like that, and this particle move from here to here, leaving this up here. And then I repeat my process, and now this particle is going to move from here to here, and leaving a trace of spin ups all the way. So after the process, I'm going to have all the particles up in this part of the state, and the other part of the state is going to remain down. So at the end of the protocol, I'm going to have a superposition of all particles up plus all particles down plus some extra doublon and a hole in this case that we don't care. It's not so important, we can filter it out. So by doing this process sequentially, you can see that I move particle at a time, flipping this part of the state with 1 up, 2 up, 3 up to create a clad state. That's a protocol, it's a step by step, and so we believe that is highly implementable. So with that, I'm running, I know that you are very tired, I have 2 minutes, so I just hope that I convinced you that alkaline air atoms have great vista ahead. So the complexity can be huge. Well, we are still too hot, but I show you about the P-wave magnetism, P-wave SUN magnetism, that was yesterday's lecture. I showed you about the spin orbit coupling yesterday. I show you, well, I didn't show you the retarded dipole-dipole interactions. This is another story that I could tell you. But I show you today a little bit of the SUN physics, of the rich Kondo physics. So there is really, really an excited set of territory to explore that interplays between many body physics and precision metrology. So I think that there is, and well, everything is collaboration. So you can see that across the years since I started at JILA, we have been able to write many, many papers together. So this is just an encouraging path for you to find a very close collaboration between experiment and theory, because this can bring the science at a speed much more faster than you are going to do if you are not collaborating. With that, of course, thanks to Junji, that has the person who does the clock, and all his fantastic group of postdocs, regular students that do the experiments, and of course, my theory group that also did amazing calculations. And thank you for all this was 6 hours of discussion, but hopefully something got into your mind, and you will remember. Thank you.